In this video, we're going to introduce the subtraction principle, which we can use together with our previous counting techniques. So sometimes it's easier to count what we want to exclude than to count what we want to include. Again, we're going to start with an example. I'd like you to think about how you might approach this, and then we'll look at it together. So suppose a door code contains 5 digits, 0 through 9. How many door codes are there that have at least some of their digits repeated? So, for example, the door code 15021, that would not that would have a digit repeated. 1 is repeated, so that would be included in what we want to look at. Whereas the door code 0, 1, 2, 3, 4 would not be included. So we do want to count things of this type. We don't want to include things of that type. So pause and think about that for a moment, and we'll talk about it together. Okay, so how many door codes are there that have at least some of their digits repeated? So one way we can think about this is, again, by counting what we want to exclude rather than what we want to include. So number of codes with some repeated digits. Well, that would be equal to all possible door codes of this type. So all door codes with 5 digits with the numbers 0 through 9, and then take away the ones we don't want. So if they do not have some of their, if it's not the case that they have some of their digits repeated, then these would be codes with no digits repeated. And we do know how to count each of these things. So this is actually a lot easier to calculate. This is easier, each of these pieces is easier than this directly. Calculating this directly would be harder. We could also do that, but it's more difficult. So let's calculate each of those pieces directly. So all door codes possible. We know that this is just a list of length 5 with no repeats. And so this is a list of length 5 with no restrictions at this point. The next part is going to be no repeats. So lists of length 5 from the digits 0 through 9. We've got our list of length 5. We have 10 choices for the first digit, and 10 choices for the second, and 10 for the third, and 10 for the fourth, and 10 for the fifth. So because these are all ands, we're going to use the multiplication principle. So we're using the multiplication principle for this. The number of possible door codes of any with no restrictions is 10 to the fifth. That's the total number of door codes. What about the number of door codes with no digits repeated? So no repeats. We know how to handle a list with no repeats. The first element in the list, there are 10 choices for it, but then there are only 9 choices possible for the next, and 8 for the next, and 7 for the next, and 6 for the next. So the total number with no repeats, 10 times 9 times 8 times 7 times 6, we can calculate that out to be 30,240. And that tells us that what we actually want, the number with some repeated, is equal to the total, that was 10 to the fifth or 100,000, minus the numbers with none repeated, that was 30,240. And when we subtract, we get 69,760. So this is what we actually want. So again, what we did was we calculated the total and then took away the ones that didn't fit our criteria, and we're left with what we want to compute. So formalizing that, here's the subtraction principle. If U is the universal set for X, like in our last example, our last example would be, for example, all door codes with those specification length 5 with the numbers 0 through 9. our X, so this is our universal set, and X is the set of door codes with repeated numbers. And then X complement was our door codes with no repeats. Then exactly what we did before, we really used this version that the value we want to calculate, the number of door codes with repeats, was equal to the total number of door codes minus the number of door codes with repeated elements. So you can use it, in either way. You could either calculate X complement or calculate X. Again, it's the number of ways X can occur is equal to the number of ways the procedure can occur in total minus the number of outcomes of the procedure in which X does not occur. So here are just two more quick examples for you to try. First, a coin is flipped 10 times. How many sequences? And remember, sequences always means ordered. How many sequences of 10 coin flips have at least one tail? And two, how many length for lists can be made from the letters A, B, C, D, E, F that contain at least two E's? So try each of these out, think about the subtraction principle with them, and we'll talk about them together. Okay, so how many coin flips, sequences of 10 coin flips have at least one tail? So again, we want sequences with at least one tail. If we want to use the subtraction principle, that would be all procedures of this type. This is the number of sequences of 10 flips. And then what do we want to subtract away? We want to subtract away all sequences in which there is not at least one tail. In other words, there are no tails. So sequences with no tails. So what are each of these values? The number of sequences of 10 coin flips. Well, there are two choices. It can be heads or tails for the first flip, 2 for the second, 2 for the third, ... all the way down to 2 for the last. So this is 2 to the 10th minus how many sequences of 10 coin flips are there with no tails? So this is just one possible sequence, right? Heads, 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 heads. And there's only one sequence of that type. So minus 1. So this is 2 to the 10th minus 1. That's equal to 1024 minus 1. And so that's 1,023 coin flips. Sequences of 10 coin flips have at least one tail. All right. How many length for lists can be made from the letters A, B, C, D, E, F that contain at least two E's? So number with at least two E's, that could be the total number of lists of this type, length for lists from those letters, minus, okay, if it does not have at least two E's, what are the possibilities? So less than 2 E's. If it does not have 2 E's, then it either has 1 E or 0 E's. If we want to, we could break this up differently. One way we could break this up is to, subtract the total number of ways that there could be fewer than 2 E's. Again, if there's fewer than 2 E's, there's either one of them or 0 of them. So we can use the addition principle or, the inclusion-exclusion principle to calculate that. Since this is or, it's going with addition. There's no intersection here because it's not possible for there to be simultaneously 1 E and 0 E, so the intersection is 0, so we don't have to worry about subtracting off the intersection. So let's think about each of these pieces separately. So first, just the total number of lists of this type. These are length for lists, 1, 2, 3, 4, with 1, 2, 3, 4, 5, 6 possible entries for each, so 6, 6, etc. So the total number of lists is 6 to the 4th power, which is 1296. The number of lists with, let's do 0 e's first because that's a bit easier. The number of lists with 0 e's. Well, now again, we've got a list of length 4, and how many possibilities do we have for each entry of the list? Well, it can be anything but e in each entry. So 5, 5, 5, 5, 5. The total number of lists with no e's is 5 to the 4th, which is 625. So what about the number of lists with exactly 1 e? The number of lists with exactly 1 e would be, well, we can break this down. So we can break this down into, first we could have a list with an e in the first entry, or have an e in the second entry, or have an e in the third entry, and you get the idea, or in the last entry. So those are the possibilities. How many of our, or again goes with addition. These are disjoint because there's only 1 e, so we can't have a list with both of these things happening simultaneously. So we've got, so how many ways can this individual one happen? There's only 1 e, so there are 5 more letters to select from. There are 5 choices for each of the remaining. And similarly here, there are 5 choices for each of the remaining, and so on. So we're using both the multiplication principle here. This is and between the, within one list, but or goes with addition, so plus for the others. So, and obviously there's just one choice here. We already selected E. So the number of selections for the first one is 1 times 5 to the 3rd, plus for this one, for the next one as well, this is also 1 times 5 to the 3rd, plus 1 times 5 to the 3rd, plus 1 times 5 to the 3rd. Or more concisely, that's 4 situations that each have 5 to the 3rd possible outcomes. This is 4 times 5 to the 3rd lists with exactly 1 e. And so this is equal to 500 if we multiply that out. And so in the end, our number of lists with at least 2 e's is equal to the total number of lists possible, and the total number of lists possible was 6 to the 4th, minus those with 1 e, exactly 1 e, and that was 4 times 5 to the 3rd, minus those with 0 e's, with no e's, and that was 5 to the 4th. And so this gives us 1296 minus 500 minus 625. And when we calculate that out, we get 171 is the number of lists of length 4 with at least 2 e's.